Welcome back. In the last video, we talked about the interaction of photons with matter at the low energy end of the spectrum. And now we're going to talk about what happens at the higher energy end of the spectrum. And that is namely Compton scattering and the photoelectric effect. And these are going to be very important for therapeutic applications. So here we go. So next we're going to look at Compton scattering. What happens in that case is a photon comes in and it interacts with the electron in the atom and is scattered. And the photon scatters off at some angle that I'll draw this way. And actually the electron also is scattered off at some other angle and with some energy. And I can draw the angles here. I'm not going to write out the equations for this, but you can write down all the equations for this. They're derived by conservation of energy and conservation of momentum, but there are two angles involved in here, and you can solve everything in terms of the energies and the angles. For our purposes, what we're going to need to know about is the initial energy of the photon coming in, and then we're going to talk about the final energy of the photon coming out and the electron coming out. And the energy is going to depend on the initial energy and the angle of the scatter. So we're going to consider a situation where the energy of the photon that comes in is much greater than the rest mass energy of an electron. And that's just going to make all the equations simpler. In the high energy regime, you can kind of simplify all these principles. So in that situation, then, what happens is you can draw things kind of in terms of different directions. So here's the electron, and if the photon is actually scattered backwards, like this, it's going to have a particular energy, and that energy is actually 0.256 MeV, half the electron rest mass energy. You can prove that mathematically. If it's scattered up to the side, like this, then it's going to have twice that energy. It's going to have 0.511 MeV. And then finally the direction is, if it scatters forward like this, it's not going to give any energy to the electron, and it's just going to come out with the same energy that it entered. It's just a grazing hit kind of a thing. So that forward scattering comes out at an energy E naught. And so in between these two, the photon is going to have some energy between 0.25 and 0.51. And in between these two, it's going to have an energy between 0.511 MeV and E naught. Then if you think about the energy that the electron gets, the energy to the electron is also going to depend on the angle of scatter. And I think it should be fairly obvious what that would be. So if it scatters backwards, that's going to impart the highest energy to the electron, because the photon has the lowest energy. Highest percent of the incoming energy is imparted to the electron. When you're side scatter, it's lower. And then when you're actually forward scattering, there's actually no energy imparted to the electron at all. It stays all with the photon. Okay, so now let's consider for a minute what happens to this scattered electron. And it's kind of a chain of events. So first, this photon initially comes in, scatters with the electron here, and the electron goes off, and it kind of collides and does a random walk in the tissue. Okay? As it does this, it can also create other photons in the process, because when a charge is accelerated, it creates a photon that is called Bremsstrahlung. the electron continues to scatter until it slows down and stops. And along the way, it can produce other Bremsstrahlung photons. Okay, now let's go back and look. The initial photon, that of course is scattered off at a lower energy, but it goes off in tissue, and then it can scatter on another electron over here, and that electron does a random walk. Again, it makes some more photons by Bremsstrahlung, and those photons then can interact with other electrons. So you can see it's kind of a cascade of events until all the energy is eventually imparted into the tissue. Okay, and then if you look at the mean range of the electron in tissue, a handy rule of thumb is that the range in centimeters is approximately equal to the energy in MeV divided by 2. So you can see how far an electron goes. That's in tissue. All right, now we're going to look at the probability that this interaction happens. That'll be quantified later, as you'll see, by the mass absorption coefficient. For now, what you need to know is that this probability of the interaction, it depends on the energy of the photon, E naught, energy coming in. And then this Compton interaction is going to depend on basically the number of electrons per gram, per unit gram. Okay, more electrons, more Compton scattering. And that's approximately the same for different materials, pretty much independent of the material type, although there's some caveats, especially materials with high hydrogen content have more electrons per unit gram, and we'll study this a little bit more detail in the next video. So now we're going to address the question of what happens when this photon comes in and Compton scatters off the electron, and in particular, what direction does it scatter off at? And there's going to be a different probability for different directions. And so one way to look at this is you can do what's called a polar plot. If the origin is here where the electron is, you have some probability of going off in some direction. And so the probability is proportional to the length that I draw this arrow at. So if I draw a longer arrow, there's higher probability. So in this case, it's very probable to scatter forward in this direction. It's very improbable to scatter this way because the arrow is shorter, and very less probable here, and so on. And so you draw these arrows like that, and then eventually what you end up with is a little surface like this, and that's called the polar plot. And so you can calculate, you can see visually. Okay, so hopefully that's clear. And now then what we're going to do is look at some different plots for different energies, and here they are. So what you'll see here is it's very energy dependent, and just to highlight a few features here, let's look first at the low energy plot. And you'll see like this 1 keV, you'll see that it's pretty much symmetric around the origin. In other words, it's as probable to scatter forward as it is to scatter backwards, and so on, right? So now let's look at the higher energy kernels. And as you go up here to higher energy, you'll see that it's more forward directed. In other words, there's less probability to scatter this way than there is to scatter in the forward direction. And you can see the surface here. As you go up in energy, it becomes more and more forward directed. And finally on the plot here, you'll see the highest energy beam. It's actually very much forward directed. It's very probable that the photon is going to scatter forward, and very improbable that it's going to scatter backwards or sideways. So there's an energy dependent probability function for the scattering angle. And that's important to remember. We're going to see it in some applications later in the course. The final interaction is pair production, where a photon comes in, and then within the field of near the nucleus, a quantum mechanical interaction happens and actually pair production occurs. So you have one electron produced and one positron produced. And of course you have conservation of energy and momentum. And so the energy of this initial photon it has to be greater than 2 times the rest mass energy of the electron, or else you can't produce this electron-positron pair. You won't have enough energy. So it has to be greater than 1.02 MeV. And then the total energy of the electron and the positron is going to be equal to the initial energy that the photon comes in with minus this rest mass energy that was created. So let's see if we can sum this all up then. I'm plotting here the mass attenuation coefficient versus energy. So that's the probability of the interaction. And then this is for photons interacting in water in this case. You'll see at the low energies below, let's say 80 keV, the photoelectric effect dominates. Above that energy, let's say between 100 keV and some MeV, the Compton scattering effect dominates. So that's important. That's the therapeutic range in there, where Compton scattering is the important one. And then at the very highest energies, you start to see pair production. Now, these effects will all depend on the Z of the material, the atomic number of the material that the photon is scattering in. So let me plot here titanium, and you can kind of see that the curves shift. Maybe more clear if I put them all on one graph together. And now you'll see that the photoelectric effect is bigger in titanium. That's that Z cube dependence. The Compton scattering effect is pretty much similar in terms of the probability. It's a little bit different because the number of electrons per gram is different. And then the pair production depends on Z as well. So these are the basic behaviors to know. All right, so there you go. That concludes the basics of photon interactions with matter. I'm going to leave you with a little bit of reading to dig into the physics more if you like. This can get quite complicated, but also quite interesting. In the next video, we're going to have a practical application of how these basic principles translate into something that's meaningful in the clinic. And we're going to talk about properties of beams, therapy beams, and also diagnostic beams. We'll see you in the next video.